we do have to go through this chapter on the periodic table. And we started talking about symbols in the periodic table, meaning, big names, if you will. Big names in the sense of some names are a little more cryptic to remember. They're not very intuitive. They're named after gods from the Greek mythology, like, titanium comes to mind. Some other names are more familiar but still somewhat obscure, like hydrogen. I mean, what does that mean? It does have a meaning. It's not terribly important for this course, but it means it generates water. Remember that I mentioned to you that some symbols have a single letter. If it's a single letter, it's going to be a capital letter. This is a little small for you to see, but I'm going to be writing some of the ones that are important on the board. Some of the symbols have two letters. If there are two letters in the symbol, then the first one is capitalized, the second letter is lowercase. But the reason why I want to show you that table is because of the color scheme that you see here. And I'm actually glad that they chose these three colors because I can see them. Remember, I mentioned to you that I'm colorblind, which doesn't mean that I don't see colors. It means that I see fewer colors than you can. So if you see 10 million colors, maybe I see 1 million colors. But here I can clearly see three different colors. And they're labeled on the bottom. I think I already asked the class if there's any colorblind person here, but I see them as blue. Maybe it's purple. I see these as green. And then I see these as yellow-orange. Am I in the right ballpark figure? I mean, those are the colors that I see. And it's not that I memorize them. That's what I see. But if there's shades of these colors next to each other, then I may not see them. Now, why the color scheme? Well, because elements, as they are found in nature, have personalities, have behaviors, if you will. So, in real life, we humans, you have people that are more introverts, people that are more extroverts, people that like to socialize a lot, people that don't like to socialize that much, and then everything in between. Well, the periodic table is more or less like that. You have, at the extreme of the table, I just want you to pay attention to what I'm going to say. This very last column, I'm going to exclude from this discussion. Those last elements on the last column are like the humans that we never see. What humans are those? The mega rich, the kings and queens, people that live in castles or in big mansions that don't mingle with us common people. I mean, that's my way of seeing that. Maybe that's not the best way, but that's my way. You pick your own analogy. But I'm going to leave those out. And in fact, I'm going to tell you that they are actually called the noble gases. At least in Spanish, that word means aristocracy. So even the name is indicating some sort of oddity as far as behavior. They're also known as the inert, and they're all gases. Now, if you notice, and you may not be able to see the numbers, they're kind of not very large, but there are 18 columns in the periodic table. From left to right, you start with number 1 at the very left, and you end up with number 18 on the far right. This guy is found in group 18, at the far right of the periodic table. A few years ago, I thought of an analogy to politics that is actually completely backwards in the periodic table. In fact, the way the periodic table is the way probably humans should be. So here you have the far left, right? We have this thing called the far left in politics. Here you have the far right. Well, in real politics in the world, they sort of like don't like to mix too much, right? In a same family, you can have somebody from the left and somebody from the right. Two siblings, one thinks one way, the other one thinks a different way. In science, in real life, in chemistry, they actually seek each other. Members of this side of the table are looking always for members of this side of the table, with the exception of group 18, because they don't mix. They live in their own world. But a member of group 1, like sodium, is always looking for a member of group 16 or 17 to mix and form a partnership. When they do, they live a much happier chemical life. That's my way of looking at it. Now, there's going to be a reason that we're going to discover later in this course as to why that happens. I mean, why is it that sodium is not happy as sodium and wants to mingle with chlorine, which is also not happy by itself? And the reason is electrons. Electrons are what make these elements either happy or unhappy. So I just mentioned something that we're going to need to explore more later today. And that's an ingredient of all atoms. Every atom in the universe has electrons. But let me go back to the periodic table. So you have these columns, which are numbered from 1 through 18. In the old days, and unfortunately are still used today, the numbers were not just 1 through 18. The numbers were subdivided into 1A, 2A, 3A, 4A, all the way to 8A. And then in this shorter part of the table, there were a subgroup of those numbered columns with the letter B. So 3B all the way to 8B. And then 1B and 2B are positioned differently. Well, you can see the problem, right? You can see that that's somewhat confusing. So we're going to try to stick with the 1 through 18 numbering system because it's a little bit easier to remember and it's more practical. But on occasion and on homework problems and quizzes, how did this move? What happened to that? It just moved by itself. When in the homework or the quiz you find a question that asks you for the old-fashioned numbering system, just look it up in the periodic table and you're going to see it. So this is going to be, in a way, your tool to answer many, many of the questions. Now, in addition to columns, which we're going to call groups, so the columns in the periodic table are called groups, we also have these rows. And they're numbered, right? So 1, 2, 3, 4, all the way to 7. These we're going to call, it moved again. We're going to call period or periods. So the 1 through 7 on the left, which corresponds to rows, are going to be called period. And the vertical ones, the column ones, are going to be called groups. So the table is divided into groups and periods. So the periods go across, the columns go from top to bottom. Now, one last thing that I want to mention before we start talking about individual atoms or atoms is the fact that, well, some groups have names actually. So for instance, the very first group has a very unique name, alkali metals. The second group has a different name, the alkaline earth metals. These guys, for the most part, we call them transition elements. They're not that well defined. They're not always predictable, if you will. These are very predictable. And then as we move, these are not named except for the last two columns, the halogens, which are group 17, and as I mentioned before, the group 18 members known as the noble gases. The three color schemes shows you essentially what I was talking about earlier. Somewhat the left-minded elements are we're going to call the metals. The ones in the far right we're going to call the non-metals. And then there's a group that is just in the middle, doesn't really care if it's a metal or a non-metal. We call them metalloids. So they may behave as both, very amenable to change their minds. These are strictly metals, these are strictly non-metals. It turns out that we can predict that if a metal is found in nature, that metal is always going to be looking for a non-metal, and vice versa. Now for the numbers inside the table. So if you notice, on top of these elements, and on that periodic table is also on top, but is slightly slanted to the left, there's a number. On top of the H here, there's a 1. And then we move all the way to group 18, and we find another element with a number 2. Both of those are in period 1. If we move to the second period, then we have element number 3, 4, 5, 6, 7, 8, 9, 10. And then it goes on and on until something happens down here that we're not going to care too much about. When we made a list last week of important biological elements, we probably included elements only between 1 and 30 or so. We really did not talk too much about elements beyond the number 30. Now, those numbers, the 1 all the way through 118 here on this table, have a name. So that name is called the atomic number. So every atom, every element, has an atomic number. This is the ID. In the United States, it's almost like the Social Security number. Only hydrogen has the ID 1. No other element has the ID 1, atomic number 1. Only helium has the atomic number 2, so it's its ID. Now, in the other periodic table, not in this one, because that's something that we'll talk about a little bit later in detail, there's more numbers, but there's a second number that is on the bottom of the symbol. So let me put a symbol here. I'm going to use hydrogen as example. So there's a 1 here on that periodic table on the top left. On this periodic table is right in the middle of the symbol. And then there's a second number on this periodic table, 1.00795. That number also has a name, and is known as the atomic mass. Sometimes it's called the mass number. Sometimes even it's called the molar mass. So it has like 3 names. Sorry for that confusion. It's not of my doing. Too many chemists involved, so they have them named 3 different things. So atomic mass, sometimes called the molar mass. Now let's stay with the atomic number. So because that is the idea of the number. Well, we're going to find out that every atom in the universe, of every element in the universe, has 3 main ingredients, 3 building blocks. And they don't change in the nature of the building blocks. Meaning, what we're going to call an electron of hydrogen is the same type of electron that we're going to be finding in helium or in lithium or in potassium or anywhere else. It's still an electron. The other 2 ingredients of all elements are the protons, and it's just a name. For now, just remember it as a name. And then finally, a third particle known as the neutrons. These 3 ingredients we're going to call the subatomic particles. I call them ingredients. You can call them building blocks. They're the components of all atoms. Now, by subatomic, the prefix sub means smaller than, so that means that they are inside of the atom somehow. We're going to take a look at the structure of the atom in the next chapter in great detail, maybe more detail than some of you may want to know, because it's really wacko. It's really crazy. It's wacky the way atoms are described by chemists. But it's the way we believe they really are. In this chapter, we're going to just stick with some very general description of every element. Now, the atomic number of any element, that number that identifies the element, is always equal to the number of protons in the element. Always. If that number changes, then you have a different element. So hydrogen always has atomic number 1, which means hydrogen always has 1 proton. There's no discussion about that. That's the way it is. The same is not true for electrons and protons. Electrons and neutrons. But we're going to talk about them very soon. Let's stay with the atomic number. So if we go to Mn, this is manganese. Atomic number 25, 25 protons. Nitrogen, atomic number 7, 7 protons. That's it. Now, what about the atomic mass? And why is it not exactly a number, a whole number like the atomic number? Well, the atomic mass, in very general terms, is defined as the number of protons plus the number of neutrons. So I'm going to call protons P, neutrons N, electrons E. So the atomic mass, or the molar mass, is the sum of protons and neutrons. But it's not a whole number. How come? Well, this is actually something that we need to explain in some detail. It's a weighted average. And I'll explain that in in a few words very soon. We just go to the next section. So let me try to explain this by looking only at hydrogen. Hydrogen is a very good element to look at because it's the simplest of all elements. So in many ways, what we learn about hydrogen can be applied to other elements that are a little bit more complicated. Now, if the atom that you discover has one proton, then it's hydrogen, right? There's no two ways about that. But there are three different sort of flavors of hydrogen in nature. So hydrogen exists in three different forms. I'm going to use a simpler notation, but let me first put the symbol for the three different hydrogens, and then I'll give you a name. So the first one has that symbol. The second kind of hydrogen has that symbol. And the third kind of hydrogen has that symbol. Why are they all three hydrogen? Well, because I probably have repeated this 100 times. They all have one proton, right? Atomic number 1. But if I made my point clear that the atomic mass is the number of protons plus the number of neutrons, you begin to see here that one of these three is a little heavier than the other. Well, now here I go with a thing that I haven't explained to you. I'll explain that next, but erase the word heavier from your brain. Just a different atomic mass for each of these. How come? Well, because this guy, and let's describe it in terms of protons and neutrons, has one proton, no neutron. Correct? 1, 1. Atomic number 1, number of protons. Atomic mass 1, number of protons, it has to be 1, right? Plus, what gives you 1? 0. So no neutrons. Still with me? Okay. This second flavor of hydrogen, 1 proton, 1 neutron. 1 plus 1, 2. So predict number 3. How many protons? 1 proton. That doesn't change. Now, what gives you 3 if you know that atomic mass is 1 plus something?
2.
So 2 neutrons are going to be needed or found in this third kind of hydrogen that exists in nature. The 3 have names. I mean, names that we are not going to use very often, but names nevertheless. The first one is called hydrogen. The second one is called deuterium. So these are, maybe we can call them nicknames. I mean, does that work? Is a nickname for the same element? And the third one is called tritium or tritium. And all 3 exist in nature. All 3 are real. You can find them in nature. However, the amount of each of these in nature is very, very different. Now, when we have an element, in this case hydrogen, with 3 different flavors or kinds of hydrogen, they're still hydrogen, we need a name for that, and we're going to call them isotopes. So these are hydrogen isotopes right here. Let me write the word isotopes. This is like learning another language, right? Learning chemistry is like learning a new language. And because I don't remember the numbers, I'm going to Google this next question. So the 3 isotopes of hydrogen are hydrogen, deuterium, and tritium. I want to ask the internet, what is the abundance of these different elements? These different, isotopes. Abundance of hydrogen isotopes. I have no idea what is going to happen. I haven't asked this question in a long time. Okay, so hydrogen consists of 3 isotopes. With something interesting here that I haven't mentioned to you. Hydrogen and the deuterium are stable. I'll explain that in a minute. Of course, it means steady. And then tritium is radioactive. So I'll explain that in a second. The natural abundances of hydrogen and deuterium are 99.9844 and 0.156. And I guess tritium is almost non-existent. So very, 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 very little.
Does every element have multiple isotopes?
Not all of them, but many of them do, yes. Excellent question, because in your chosen profession for some of you, if you're going to become a nurse, in the treatment of certain diseases, like for instance cancer, you use these radioactive elements, which are typically isotopes of other elements. So you have these, which brings me to a really interesting question about the periodic table and the noble element. No, it's not there. The periodic table and something called radon. Have you ever heard of radon? If you haven't heard of radon, you're going to hear me today for 3 minutes. I promise not to go much longer than that. Because radon is radioactive. So one of the isotopes of radon. And radon is a gas. And unfortunately, it's a gas that, because of its radioactivity, can actually, it's almost like smoking, can create lung cancer, for instance. And it's super abundant in this part of the world, in New England. So where I live, in Tiverton, we had to install a system for radon mitigation, to remove radon, because our basement sips radon in huge amounts. It's just part of the crust of the earth. It just resides there, and it's almost like the earth is burping radon. So when earth burps, radon comes out among other gases, and you don't want it at home. Sadly, probably is not something that everybody is aware of, and sometimes you live with radon without even knowing, because it has no smell. Your eyes don't burn. There's no way of knowing that you have it unless you have a radioactive detector specifically for radon. Now, I don't know about Fall River. Let's just, this is all useful, I hope, for your health. I didn't even put Massachusetts. So there's a MassGov website. Let's go. It should be somewhat trustworthy. There's an explanation of radon. I just wanted to see if there were numbers here. So is exposure to radon harmful? Yes, radon is a carcinogen. You know, I don't want to take too long of a detour, but I guess it's not that abundant. I mean, certainly not compared to smoking. But 750,000 almost of homes have radon levels that exceed the safe levels that should exist at a home of 4. This little p is pico, which means 10 to the negative 15, I think, in the metric system, 10 to the negative 15. And then this CI means curie, which is a unit of measuring radioactivity. So you measure radioactivity, just like you measure length in meters, you measure radioactivity in curies. I have 3 monitors at home for radon. And I start freaking out whenever I see it go to 4 or higher. But it's the long-term average that you should be concerned about. It is because there is an isotope of radon that is radioactive. So in the case of hydrogen, going back to my discussion, tritium is radioactive. But there's so tiny amounts of it that it doesn't really matter. As it comes, it goes. In other words, it gets destroyed and reformed constantly. This is not the place for me to discuss how radioactivity works. In a future lecture, we may be able to take a look at that. But suffice to say that if hydrogen has no neutrons, is hydrogen. If hydrogen has 1 neutron, is deuterium. And if hydrogen has 2 neutrons, then it's tritium. What about this number? Where is that coming from? Well, I mentioned to you something like weighted average. And let's start looking at that in the most practical and perhaps simple way. Let me see if I can pull this open right here. So I'm back at your course, and I'm looking at the syllabus. I hope it doesn't take forever to open. And I'm going to scroll down here to this table. So at the end of this term, everybody's going to get a grade in this course. Everybody's going to get, I hope, a really good grade. But that grade is calculated by considering different percentages on the different things that you are doing to be evaluated. So every week you do a quiz and a homework. Those two combined, which you have ample opportunities to do well, 50%, 25% and 25%. The exams, there's 3 of them. Each one of them is 10%. Here is where I try to determine, the A pluses from the A minuses, a grand total of 30%. And the labs, which is guaranteed that if you complete this course, you're going to get 100 there, is 20% of that. Now, what does that mean as far as the final grade? Let's do an imaginary calculation here, because then we're going to use it for calculating the weighted average of hydrogen in this case. So this is my quick explanation of a weighted average. Quizzes, homework, lab. I'm going to call this the weight. And here the contribution. Two columns. Now, exams 30%, quizzes 25, homework 25, lab 20. Grand total 100. Now here comes the calculation, and this is what is going to be useful to us to figure out this number for this hydrogen. So you take 3 exams and you get on each exam a 90, 90, 90, 90, right? So the average, everybody understands what an average is. Not a weighted average, but just an average. 90 plus 90 plus 90 divided by 3, 90. So what we're going to do is we're going to multiply 90 times 30%. Now percentages, because we learned this earlier in this course, you can either do the long calculation or you simply say, oh, 30% is actually 0.3. So times 0.3 is going to give me the 30% of 90. So 30% of 90 is calculated by multiplying 90 times 0.3. So that's 27. So there are 27 points contributed to your final grade from the exams if you have 90s on all 3. Let's say that your quizzes are also a 90. The homework is 100, and the lab is 100. In fact, let me change it a little bit, just so that you see how it's not that important to get 100, 100, and 100 everywhere, right? Let me change this one to 80. So you don't do very well on the exams. Oh my God, that's a B. I'm going to get a B in the final grade. But it's only 30% of the grade. So 8 times 3, 24. Now, 90 times 25. Oh man, I'm going to need a calculator. What was it?
I lied, I'm sorry. What is it,
90 times 0.25.
90.25?
So it's like divided by 4. 22.5. And then 100 times 0.25 is 25. And times 0.25 is 25. So if I add those 4 numbers, I get the weighted average for this course. So what is it? 50, 72.5, 76.5, 96.5, right? No? Am I doing something wrong?
The labs are only supposed to be 20.
Oh, oops. I was going to get a higher grade. 0.20. Okay, so what is that? Help me out with the adding. 0.5, 5, 7, 11, 91.5, right? So even though you only got a B minus on the 3 exams, you end up with an A minus in the final grade. Well, not happy, right? I mean, we want an A plus, but that's my example. That's a weighted average. We're going to do the same thing and see if we can come up with a number close to that for hydrogen. So according to the internet, we're going to change this to final weight, final mass. And we're going to replace these numbers by hydrogen, deuterium, and tritium. Those are the 3 contributing factors to the mass of hydrogen, right? Now, hydrogen contributes, instead of the exams being 30%, in this case, the hydrogen is 99.9844%. 99.9844. Oh God, I don't have a good memory today. Did I get it right? Yeah. Deuterium only 0.0156. This 0. So now if we do the math, we're going to do it exactly the same way as before. We're going to say, okay, so now here's the thing. We need to look at the mass of each of them, because that's the grade. The mass of each individual atom, isotope, is the grade, if you will. So the contribution of hydrogen is 1, right? Because that's the mass of this hydrogen by itself, mass of 1. The contribution of deuterium is 2, because that's the mass of deuterium. So here I'm going to put mass number so that you know what I'm talking about. And the contribution of tritium is 3, because that's the mass number of tritium, 3. Now, that times this in decimal, so that times 0.9998844. Notice that I'm just moving the decimal place 2 spaces and multiplying that. Is going to give me that contribution. Two times 0.000156 is going to give me that contribution, and 3 times 0 is going to give me that contribution. So I'm going to trust your numbers. If you could multiply 1, well, I guess that's 0.999, 0.99984, 4. And then 2 times that. What is that? 0.0000312. And then 3 times 0 is 0. Let's add them together. Boy, I don't know if I line them up right. Okay. 6, 5, 11, 10, 10, 10. I come up with 1.00156. Not quite the number on the periodic table, but it's close. And I think you probably get the idea. So the number in the periodic table is this number that I put here, 1.00795. I'm coming up with 1.000156. That's based on some random place in the internet that is telling me that this is the abundance. If I look somewhere else, I may get different numbers. For instance, this is a Wikipedia. Yeah, I'm already seeing that this is different. Look at this. Abundance. It's actually slightly lower, but it's still different. But you get the idea, right? You understand now 2 very important concepts. The fact that the atomic mass of any element is a weighted average if there are isotopes, and how to do that weighted average in very general terms. Of course, we're going to need practice. We're going to do it together when we do the homework. This is just the background. So any questions before we look at other elements and start making predictions? Yes, please do. Very good. We're going to go there next. What about electrons indeed? And the answer to that question, I mean, I was actually heading that way, so thank you for bringing this full circle. So I'm going to erase this for now, and we're just going to concentrate on the idea of electrons. We need a little bit more information regarding these subatomic particles. So we're going to create a table with some descriptions of those particles. we're going to describe something called the electrical charge of each of these three. And I'll explain that in just 1 minute. And the mass, the weight of each of those three. So they're not weightless, right? I mean, they exist. They must have a mass. Now, what is electrical charge? Well, we're not going to get into a huge discussion of what electricity is. But you know a battery, right? A battery has a positive end and a negative end. We're just going to go with those two values, and we're going to call them charges. So either you can have a charge of 1 or a charge of -1. The electrical charge of the electron is -1. It has a numerical value of 1, but it's negative. Okay? So electrons are negatively charged, and each electron has a charge of 1, but it's negative. The protons are not neutral either, just like the electron. They have a charge of 1, but that number is positive. So protons are positively charged. Okay? And guess what? The word neutrons should tell you neutral. So electrical charge of neutrons, 0. They don't have a charge. They're not positive, they're not negative. Now, when it comes to the mass, it's a little tricky, but you're going to have to take my word for this. If I Google the mass of a proton, you're going to find that the scientific notation is actually useful because the number is so small in grams in kilograms. Check this out, 1.67 times 10 to the negative 27 kilograms. So imagine 26 zeros in front of a decimal point, after the decimal point, and then a 167. That's really not very useful. So the mass of a proton for this course is going to be in a new type of unit called the AMU, the atomic mass unit. This is just a convenient number. And just so that you know, 1 AMU equals this number, essentially. So we're not going to write it down. We're just going to say that the mass of a proton is 1 AMU. That's how much it weighs. Is that understood? We're just going to call it 1. Mass of a proton, 1. The mass of a neutron is a little bit different. Tiny, tiny bit different. But it's so insignificantly different that I'm going to tell you, trust me when I tell you that a neutron weighs the same as a proton. They're just as heavy. The same mass of a proton is the mass of a neutron. No two ways about it. Now, please don't write this down because I'm going to erase it. But the mass of an electron is 1 divided by 2,000 the mass of a proton. In other words, you need 2,000 electrons together to weigh equal to 1 proton. So because that number is so small, although you know now that this is not completely true, we're going to take a liberty, we're going to make our lives easier, and we're going to say that the mass of electron is 0. For the purposes of this course, An electron has no mass. That's a fallacy. That's a lie. They do have a mass, 1/2000th of a proton, of 1. 1 divided by 2,000. But to make our lives easier, because they contribute almost nothing, we're going to say 0. Okay, now we're getting to the question of what about electrons in an atom, in an element? Well, let's make a little table here. So we're going to have hydrogen, helium, lithium as 3 examples, and we're going to make a table. So atomic number, atomic mass. This is going to be our predicted mass, charge, number of protons, number of neutrons, number of electrons. So it's a long table, but it's going to explain the number of electrons on an element as compared to the number of neutrons and protons. So according to the periodic table, the atomic number of hydrogen is 1, right? According to the periodic table, the atomic number of helium is 2. Because if we look at the periodic table, that's the atomic number that appears for helium. I'm going to use that table so that I don't have to go back. So there's a big 2 on top of He. And then Li, atomic number 3. So I'm just going to put it here. Now the atomic mass, I'm going to use the stuff from the periodic table, but I'm going to round it to a simple number. So 1.008. So I'm simplifying things. For helium, according to this table, is 4.00260. So I'm just going to call it 4.00. And for lithium, according to that periodic table, is 6.941. So let's call it 7. These are not, they're rounded numbers. Now, the charges of the elements, when you find them in the periodic table, are always going to be 0. That's going to be different in a future chapter. But from the periodic table, if you look at an element in the periodic table, the charge is always 0. And we're going to see what that means very soon. The number of protons. You should be able to complete this column without me even saying anything. Can you tell me the numbers that I put here for the number of protons for hydrogen? How about helium? And how about lithium? Absolutely correct. Number of protons equals the atomic number. No two ways about it. Now, the number of neutrons, we're going to base it on this number. And let me just erase that 8. It's distracting me. You can erase it from your notes if you're taking notes. But the atomic mass is 1. So we're going to say how many neutrons? 0. Because the number of neutrons plus the number of protons gives you the atomic mass. In this case, is 1, so there can be no neutrons. Here comes the answer to your question, the number of electrons. From the periodic table, when you look at the periodic table, the number of electrons for any element in the periodic table is equal to the number of protons. So if you have 1 proton, you have 1 electron. Can you prove that, Professor? Yes. 1 proton, charge of +1. 1 neutron, charge of -1. 1 plus 1 minus equals 0. If you add 1 to minus 1 gives you 0. So to make your life easy, for now, because later when we talk about ions, it's going to be a little different, the number of protons equals the number of electrons. So let's complete that. 2 electrons, 3 electrons. Now the neutrons. If the number of protons is 2 and the mass number is 4 for helium, I heard 2, that is correct. 2 plus 2, 4. That's the 4. For lithium, you have a 7 atomic mass with 3 protons. So it has to have 4 neutrons. 4 plus 3 gives you that 7. Now lithium does have isotopes, so that's why the number on the periodic table is not 7, it's 6.941. So obviously there's different isotopes. We're going to do a couple of problems next Thursday. Do you add?
You always add it to find that, the neutron?
Yes. Add or subtract. Now, I'm going to give you an incomplete table, and we're going to talk about what that means. Now, there's a section of the book that describes the experiments that were conducted to discover these things that we're talking about. So there were some experiments that had to be conducted to discover the charge of the proton, the charge of the electron, and the charge of the neutron. Read them at your own risk, if you will, because they can be a little confusing. We don't need them. We know that what Rutherford and J.J. Thomson and a few other scientists discovered happens to be true. So I'll just take it as gospel. Here in the table that you see here, they do assign a mass to electrons, but we're going to be saying 0, we're going to be saying 1 and 1. Now, here we go to a brief discussion of something that we're going to explore in more detail in the next chapter. Any questions about now how to predict the number of electrons, protons, neutrons, etc.? Okay. So it is amazing that in 2024, if we search for the word atom, we may still see pictures like this. In fact, you probably can buy coffee mugs and T-shirts that have that. Do any of you recognize that little cartoon? I mean, I can put it here. And then just go to images, and there they are. There it is, there it is, there it is. That's totally wrong. Even for a Chem 090 course, which is supposed to be a basic introduction to chemistry, we're going to say and reject, that's not the way it is. Not only the scale is bad, but the fact that is implying that the electrons are moving in this orbit. Everybody knows what is an orbit? You know, the moon orbits around Earth. It's completely wrong. There's a better model, not perfect, but better, and you see it here, so I'm not going to draw it. Is this one right here? This one right here? So instead of these elliptical things, you have circles. This is the best model of the pictures that you see here of what goes on. So I'm going to use a combination of those two when we talk about the structure of the atom. But right now, I have to give you some perspective. Before the perspective, I hate to use examples that not everybody's familiar with. But don't be shy and raise your hand if you have never been to an American football field. So you've never seen an American football field? Yeah. If you've never been to one, you're not going to have any idea of the dimensions. The next one is even worse. What about a golf course, where you play golf? Many of us have never been, well, I have been to a few, but some of you may have never been to one. Well, let me just tell you that the golf course is much bigger than the football field. So I'll use the football field as my analogy. But I need to rely on the golf course for something. Now, imagine a football field. We're going to call this the size of the atom. Hydrogen. Hydrogen has that size. It's as big as a football field. The proton of that hydrogen is going to always be found, forgive me again, at the 50-yard line, whatever is in the smack in the middle. So right here in the middle, right here, in a very small part of the field, you're going to find the proton. The proton doesn't move from there. We call that the nucleus. So this whole thing is the atom, the football field. Now, what is the size of the nucleus compared to the entire size of the atom? Well, maybe the size of a football ball. The ball that they play with is probably the size of the nucleus. So you put the ball in the center of the field, and all of the rest is empty space, right? Protons are only found in that area. Neutrons too. So the nucleus has protons and neutrons. Where are the electrons found? Well, hydrogen has only one electron, right? We agreed to that. Well, here's where the electron is going to be found. Here, or there, or there, or there, or there, or anywhere in that football field. And the size of the electron, well, I don't think I can fit 2,000 golf balls in one football. So it's even the size of a marble. Think of a marble. If you ever seen a marble, oh my God, maybe you've never seen a marble. What, a bean, a tiny bean that you eat, or a rice, a grain of rice. That's the size of the electron. Super tiny. Okay? Question?
All right. So the hydrogen is the football field, the protons and the neutrons are the nucleus, and then the
Electron
is freely running.
is freely running through the entire football field.
What's being done in all the empty space?
Say that again?
What's being done in all the empty space?
Nothing. We humans are almost empty space. It's really, I'm telling you, next chapter is wacko as wacko can be. Not only that, just as hydrogen has one electron, well, we have millions and millions and millions of hydrogen atoms in us. They're all combined with other atoms, carbon, oxygen, etc. But the electrons in those hydrogen atoms and carbon atoms could be in that football field, more of that later. Or they could be taking a trip to Japan and then coming back. We lose electrons and regain electrons all the time. We don't even see them. So it's really crazy. I mean, it's almost like they were using some acid or something when they came up with these ideas. I'm telling you. Okay, now, you see this image right here? Why I picked it as the best? Because I hope you can see right at the center is the nucleus. So that's the nucleus. In this case, you have 2 protons and 2 neutrons. Just an example. But all of this shaded area is where the electron can be found. The darker the area, You can see how it's darker towards the center and lighter towards the outside. The greater the chances that the electron is found there. So even though I told you that the electron can be found here and there and there and there, and it's constantly moving, 99% of the time it's going to be found hovering around the nucleus. And then less likely to be found here, here, or there, or there, or there. But it could be found in Japan, in China, in Africa, anywhere. Yes?
Is there any time where the electron has a lower probability of being near the nucleus?
Well, that's not improbable, so yes. And
Is it ever more likely to be somewhere further away from the nucleus than closer to it?
the likelihood of the electron being somewhere else closer than the neutron exists, but it's not more likely. So if I understand the question right, yes. Unless you start messing with them, exciting them. And when you turn on the light, there's something analogous to that. I mean, that's a beautiful question. Great question. We're going to have a good time when we talk about chapter 5 and the atom. But at this point, what I want you to know is just that the location of the protons and the neutrons is in the nucleus of the atom. The electron is found in what we can call the space around the atom, the orbit. We're going to formalize this later. And, well, that's all for today.